All right, everybody, last video. This is problem number 4 on calculating with friction, and we're going to see if we can make sorts and sense of this problem along the way. Let's start by reading it and annotating to make sure that we've got all the different pieces. So on this particular problem, it starts out and it tells you that a 65 Newton boy, right, is sitting on top of a sled that has a weight of 52 Newtons. So both of these two things are kind of together as one entity, even though right now they're written as two. On a horizontal surface. So we're talking about on a flat surface, just as it was, which is good. It says the coefficient of friction between the sled and the snow is 0.012. That's a lot less than we've had so far. There's a lot less friction between snow and sled kind of skates. What is the magnitude? That's the amount, right, of the frictional force. This is what we're looking for. All right, so we're going to start with that. And then it also has this secondary piece in there. Sometimes physics problems ask this little extra bit, but we need to solve this first part first in order to get there. So I'm going to leave that second part kind of off for a moment. We'll answer that at the end. So let's go ahead and annotate. We're still coming along the way. And it's these two parts up at the top. This is a force of gravity here. It's the 65 Newton boy, so it's a weight. This is a force of gravity here. That's also a weight, kind of pulling down. This is a coefficient of friction here. And then we're looking for the frictional force is what we want. So we've got these different parts and pieces that are kind of outlined in the problem here. And we're solving for the frictional force. All right, so equations-wise, the frictional force one means that we're going to be using this coefficient of friction is equal to the force of friction over the top of the normal force. And this is starting to sound pretty familiar because we can rearrange this equation to be able to say that the force of friction is equal to the normal force times the coefficient of friction. We've now done this in the last few problems, so those are both the same. Equation just reworked algebraically. But since we're solving for the force of friction, as long as we can figure out what our normal force is and what our coefficient of friction is, we're good. And we already know the coefficient of friction, so all we need now is the normal force. All right, if we look at a free body diagram of this, and we're saying here is kind of the boy and the sled. So this is like boy on sled. If that's the case, the boy is down here at a certain amount of gravity pulling down that way. And I could put another arrow drawing next to this one to kind of show this one's for the boy. Or I can add them kind of one next to it like that. So this is kind of my total downward force. And I'm going to just kind of stack them up like that as things go. So this is the force of gravity for the sled. We've got two pieces there of the boy and the sled all pulling down on each other. We know this is on a horizontal surface, and so we also have the ground pushing back up again, and so I'm going to go ahead and drop that one is in here. And it has to be equal now to both the boy and the sled because the sled's not getting sucked down into the snow that we know of, and it's not being thrown high into the air, so we're going to go ahead and call this the normal force. So if we can go ahead and just say, hey, check this out, the boy's gravity and the sled's gravity at that point equal the normal force. And if I know the normal force, I can multiply that times the coefficient of friction. I got it. I got my force of friction. So all I really need to do right now is I need to sum these two forces. Oops, that's not a very good circle. Sum these two forces here to be able to figure out kind of what to do. So let's go ahead and plug in the values that we've got. We've got 65 newtons for the boy, and we've got 52 newtons for the sled. So the total downward force, if we're going to add these two things together, well, 60 plus 50 is 110. 5 plus 2 is 7. So I've got 117. So my total downward, right, if we're thinking about it that way, my total downward force, the sum of my forces in the down direction, is 117 newtons. That's my total down. Sometimes people do this by saying, what is the sum? This is sigma, sum of all of the forces in the y direction. And we just go ahead and equal that and saying, well, it's 65 newtons plus 52 newtons. You might see this written sometime. This is the sum of sigma of the forces in the y direction is equal to the two forces downwards as we go. And of course, it also has the force upwards, which would be the force of the normal, which would mean that your total up and down would be 0. But I'm really focused on kind of the gravity side of things, so we'll leave it as such. All right, so I've got 117 newtons downwards. That's going to be equal now to my total amount of force upwards. So I'm going to go ahead and kind of erase this arrow, making sure that I know what I'm talking about clearly, and say that these two things sum together to 117. That's probably better. That sounds better. All right, so if I come over here to my newtons at the top, I know this is also going to be 117 newtons. And let's go ahead and plug that into our equation right here. So I can say my frictional force is equal to my force that is normal times my coefficient of friction, and I've got 117 newtons, and I'm going to multiply that 117 by this 0.012, no units on that, and this is going to be my frictional force, which is the first part of that problem. So I've got 117 times 0.012, and now my frictional force comes out to be 1.4, 1.404, but I'm going to leave it as 1.4 newtons. That's my frictional force. Am I done? Well, kind of. I said, what is the magnitude of the frictional force? So this is kind of my first thing. My first answer is already done. That's my frictional force. Secondly, it tells me up here at the top, it says the sled is pulled at a constant speed by a rope held horizontally. What is the tension, the pull of the rope? All right. Well, let's go ahead and put in our arrows to show this. This is the pull, or what's being applied. And here's my frictional force. And it says this important thing here. The sled is being pulled at a constant speed. If it's a constant speed, that means that there's no acceleration, which means that all the forces have to sum to 0 in order to make this happen. Well, if the force of friction is back here at this 1.4 newtons, that means that over here, the force that needs to be applied to it is also going to be 1.4 newtons because they need to cancel each other out. So the pulling force in the end, the tension on the rope being pulled, that's just the force in the rope. The tension is also going to be equal to the force of friction, but in the opposite direction, right? And that's going to be equal to 1.4 newtons. No additional calculation needed, just understanding what is going on in the problem itself, recognizing that if there is a constant speed, therefore those two forces must be equal, and the tension in the rope pulling must be equal to the frictional force. That's problem number 4. I hope that made sense, and I'm going to go ahead and stop this video. We'll be giving you some problems tomorrow, which might be today, depending on when you watch it, and hopefully these will help you to make sense of those problems. All right, everybody, take care. See you next time.